Now, at this point, we've got the basic rules of how carbon and hydrogen atoms are attached to each other in organic molecules. It turns out that there are many, there are millions and possibly, probably billions of organic molecules out there in the world, and you can group them into different types, into different classes. So we're going to talk about our first type of organic molecule. The name of this group of organic molecules, or this class of organic molecules, is called alkanes. These are the simplest organic molecules. I put simplest in quotes because even they can become relatively complicated. Alkane molecules only contain carbon and hydrogen. They don't contain oxygen or any of the other possible atoms that I said could possibly be found in organic molecules. Alkanes only contain carbon and hydrogen. Sometimes they are called hydrocarbons because the hydro in hydrocarbon stands for hydrogen, which alkanes have, and the carbon in hydrocarbon stands for carbon, obviously. Alkane molecules have all single bonds. So some of the molecules that I showed you in the previous section had double and triple bonds between the carbons. Alkane molecules all have single bonds at each particular atomic attachment. Alkane molecules are often used as fuels. Their names, they have, each type of alkane molecule has a name that ends in the letters ANE. You may have heard of propane and octane. So if you have a propane grill where you put gas in your tank and the type of gas is measured with an octane rating, these names, propane and octane, are names of specific types of alkane molecules, and we'll talk about that in a little bit. This is a list of the 10 simplest alkane molecules. There's methane, which you may have heard of, ethane, propane, butane, and basically one thing that may be useful at this point is to write these down. Actually, don't write them down quite yet. I have a slide. The next slide, I think, will show this in a nicer form. But this methane is the simplest alkane, and then they proceed off to the right as slightly more complicated alkane molecules. And I'll describe what I mean by that on the next slide. So the simplest alkane I said was methane. It turns out that methane has only one carbon, and its formula is CH4. So this may be familiar. This was the first molecule that I wanted you to describe the attachment of the atoms in the previous section. So, and when we did this exercise, I said, look, this is the only way that you can draw the attachments of the carbons and hydrogen atoms in the molecule whose formula is CH4. Turns out CH4 has a name. It's called methane. So methane is the simplest alkane. It has only carbons and hydrogens, only single bonds between the carbons and hydrogens, and it only has one carbon. Ethane is the next simplest alkane. It has two carbons, and its formula is C2H6. And it turns out that if I just showed you this formula and asked you to follow the rules that we described in the previous section, this is the only way that you could draw the structure or the attachments of the atoms in C2H6. So this is the structure of an ethane molecule. And then they get progressively more complicated by adding one carbon each time. Methane has one carbon, ethane has two carbons, propane, which is the next most complicated alkane, has three carbons. And you can see it drawn here. Carbon, carbon, carbon. And then, again, they get progressively more complicated. Butane has 4, pentane has 5, hexane 6, then heptane 7, octane 8, nonane 9, and decane 10. These I want you to memorize, and we'll talk about a little bit more about memorizing these in a little bit, but I want you to be able to sort of commit these to memory and recall them. At this point, what I would do is, because we're going to refer back to this list throughout the rest of the unit, is I might write these down, that methane has one carbon, ethane 2, etc., on a sheet of paper so that you can refer to it as I ask questions throughout the rest of the unit. But hopefully you can see that these are all alkanes. They all contain only carbon and hydrogen, and they all only have single bonds. And then they get progressively more complicated by attaching one additional carbon at each point. And I'm not drawing out heptane, octane, and these others just because it gets a little bit relatively large and a little bit tedious to draw out. So hopefully you can see the pattern emerging here. It turns out that there's a problem with the rules that we laid out in the earlier section, and a problem as how those rules relate to the alkanes. So obviously there always has to be a problem that needs to be solved, and let me try to illustrate the problem here. Pretend that I came up to you and I said, look, I'm working with a molecule, and the formula for this molecule is C4H10, and I would like to know how the atoms are attached to each other. And then you, knowing the two rules that we discussed earlier, you know that you basically break out your pencil and paper and you say, look, it has to be like this. 4 carbons, because the C4 means 4 carbons, they have to be attached like this, and it has 10 hydrogens. And there are the 10. And I'm not breaking any of the rules. Every single carbon makes 4 covalent bonds, and every single hydrogen makes 1 covalent bond. So what's the problem? There is no problem, right? It turns out, however, that I don't have to draw the attachments in this way. I could draw the attachments like this, like the cartoon molecule that I'm showing off to the right here. And I still have the same formula. There are still 4 carbons. 1, 2, 3, 4. There are still 10 hydrogens. There are 3 here. Another 3 make 6, 7, and another 3 here make 10. So I have the same simple formula for this molecule, and I am meeting all of the requirements. Every single carbon makes 4 covalent bonds. Every single hydrogen makes 1 covalent bond. And yet, this molecule here that I'm circling off to the left is not the same thing as this molecule here that I'm circling off to the right. They may have the same simple molecular formula. They may both be C4H10, but they are actually completely different types of molecules in real life. This one has a different boiling point than this one has. This one burns in a different way when you set it on fire than this particular molecule. They are completely different in their behaviors. So if I came up to you and I said, look, I'm working with C4H10, you don't know whether I'm talking about this particular molecule, which is called butane, or whether I'm working with this particular molecule, which is called something else completely and has a completely different behavior. So that's the problem in a nutshell. The rules that we set out very early in this unit work for very simple organic molecules. But once the molecules get larger, once they reach about 4 carbons in length, then you begin to have problems in understanding what type of molecule you're talking about when you are only presented with the simple molecular formula. If I say I'm working with C4H10, you don't know if I'm talking about this or this molecule over here. If I say that I'm working with C5H10, maybe I'm working with this molecule, which is called pentane. But it is possible to rearrange these carbons so that they have branches. So this carbon shooting up here to the north is called a branched carbon, because these 3 carbons, you can think of them as being in a line, but then there's a branch in the line, and there's a 4th carbon coming off of the branch. Here all the carbons are in a line, in a relatively straight line, and here they're branched. The same is true once you start dealing with larger and larger organic molecules. 5 carbons can be arranged with branches. 6 carbons can also be arranged with many different branches. And it turns out that the larger the number of carbons you have, the more possible combinations you can have for how you can attach these carbons to each other with and without branches. So the idea is that C4H10 is just the beginning of where the problem shows up. It just gets worse from there once you start dealing with larger and larger organic molecules. So the problem needs a solution. We need to find a way to distinguish between chemicals with the same simple molecular formula, but when those chemicals or molecules have different atomic connections or different atomic arrangements. So if I tell you I'm working with C4H10, I need a way of distinguishing between this molecule here and this molecule over to the right. At this point, I want you to realize that we have been discussing, I've been showing you different ways of describing a chemical, an organic molecule. The first way, which we actually learned very early in the course, is to describe molecules using a simple molecular formula. So CH4 is an example of a simple molecular formula. And the problem, obviously, that we just pointed out in the previous slide, is that even though they're simple, they're relatively easy to write out, they can become ambiguous once you start to deal with larger molecules. So C4H10 is a molecular formula, but it doesn't tell you which type of C4H10 molecule you're dealing with. And I showed you the two possible C4H10 molecules on the previous slide. So molecular formulas are one way of describing a molecule. They're simple. That's a nice advantage that they have, but they can be ambiguous. In other words, when we're talking about C4H10, do I mean this molecule here or this one over here? You can basically say, well, why don't we solve that problem by drawing the molecules out the way that we've been drawing them? The way that we have been drawing them is technically called an expanded structure. So with an expanded structure, you write every single atom out, and you write every single attachment that every atom has to every other atom that it's attached to. And so in this case, this is one form of C4H10, and this is the other form of C4H10. So one way of solving the problem is to say, look, I'm going to make a rule. I'm going to forbid using simple molecular formulas, and I'm going to force everybody to write out all of the attachments like this. And this is we're going to call this an expanded structure, and then no one will ever be confused, because if you will be prohibited from saying that you're working with C4H10, you'll always have to draw this out. Or if you're working with this version of C4H10, you'll have to draw that to whoever you're talking to. And this is just another example of an expanded molecular structure. The problem with this, the advantage of this is it's completely unambiguous. People know exactly what you're talking about, what type of molecule you're talking about, if you draw the expanded structure. Unfortunately, this is incredibly tedious, and people get sick of drawing these things, especially when the molecules become larger, and they can become significantly larger than the one that I'm circling over here. The problem is that it becomes a gigantic pain to draw out expanded structures. These are shown a lot in introductory texts, but for the most part, people don't do this, don't draw out expanded structures as they progress in chemistry. So I'm pointing out here that expanded structures, I'm saying it's a gigantic pain. So is there a better way? Is there an unambiguous way that isn't quite as tedious? Well, it turns out there is. There are actually a handful of them. The first way that is unambiguous but less tedious is called a condensed structure. So condensed structures, again, are unambiguous. They're less tedious. That doesn't mean they're completely untedious, but they're a little old-fashioned. And I'll show you what I mean by a condensed structure. This is an expanded structure. This is the expanded structure for butane, 4 carbons, so C4H10. The condensed structure basically says, look, I don't want to draw every single attachment to this carbon. I want to treat every carbon as its own little chunk, and whoever it's attached to, I'm going to write a sort of what I would call a mini formula. So this carbon I'm going to treat as a chunk. It has 3 carbons attached to it. So I'm going to write this as CH3. And so this carbon being treated as a chunk is written like this. It's written as CH3. Then this chunk is attached to another carbon, which is treated as a separate chunk. And you draw a little dash there and say, look, the first carbon is attached to another carbon. This carbon here has 2 hydrogens attached to it. So I'm going to call that CH2. This carbon here is attached to another CH2, so I'm going to draw a dash, and I'm going to draw another CH2. And then finally, this third carbon is attached to a 4th carbon, which has 3 hydrogens, so I'm going to draw a dash and a CH3. And this is called a condensed structure, and obviously in comparison to the expanded structure, it is condensed. And hopefully you can appreciate that this is a little bit less of a pain to draw out than this is. And so that's very nice, and condensed structures were basically devised to avoid having to draw out these types of expanded structures. And if you wanted to, this is 1, 2, 3, 4, 5, 6 carbons, it's hexane. If you wanted to draw out the condensed structure for hexane, you would basically follow the same rules. This is a CH3, so we draw the CH3 there. CH2, 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 and then we end in a CH3. So again, you can see that it's significantly easier to draw than the expanded structure. And you might ask, well, how do I draw the other version of C4H10, which had the branch in it? So here's the expanded structure of the other version of C4H10, 1, 2, 3, 4 carbons, but it has this branch. It has this carbon branching off of the middle carbon over here. How do you draw that? You basically draw it the same way. You treat each carbon as a chunk, so there's going to be a CH3 attached to a CH, and then you draw a new chunk pointing up to the north. So the way that you would draw the expanded structure for this version of C4H10 is you would draw CH3 dash CH dash going up to the north, CH3, and then another dash to another CH3. And this is the condensed version of this. So this is relatively nice, and a lot of people use condensed structures to this day. You will also often see this in introductory texts. A lot of times if you look at the prescribing information for medicines, a lot of the chemical structures of medicines tend to be organic molecules, and they are very often written in this way as well. They're written in the condensed way. Sometimes they're actually written in the expanded way as well, but that's less common. So condensed structures are relatively nice, a little bit easier to draw. It turns out that once you get to even larger molecules, however, even condensed structures can kind of be a little bit of a pain. And if you were forced to draw out larger types of organic molecules, you would see that you would soon get sick of drawing the letter C and the letter H and all of these attachments. So it turns out that there is sort of an even simpler way of drawing these types of molecules, drawing these types of attachments in an unambiguous way. So this other, even simpler way than a condensed formula for unambiguously describing organic molecules is called a skeletal formula. I'm not going to go into the details right now. I'm going to save that for the next section because it's relatively detailed. But what I want you to realize is that this is an even simpler way of drawing the attachments in atoms in organic molecules. It is unambiguous, it is kind of minimalistic, and it's a little bit weird, so it gets its own section. There is one additional way that can be used for describing molecules unambiguously. So we said that sort of drawing the molecular formula can be ambiguous when you get to larger numbers. Another way of unambiguously describing molecules is to give each unique molecule a unique name. So I'm just calling this right now, I'm calling it unique naming of molecules. This will get a couple of sections as well in this unit. It's unambiguous. It turns out that there's no drawing involved. You just give each molecule, each unique type of molecule, a unique name. So it's just giving everything a name. As an example, over here I said, look, CH4, this is the only way you can draw it. Its name is methane. C2H6, this is the only way that you can draw the attachments correctly. It has its own unique name, it's ethane, and etc., etc. Unfortunately, when you get down to here, to C4H10, you don't know if you're talking about butane, which has all the carbons in a single line, or whether you're talking about the other thing that I talked about previously, this thing over here, which is not butane. So the idea behind this approach to describing molecules is to give this a different name, its own unique name that distinguishes it from every other type of molecule, and especially distinguishes this from butane. The other thing, so the idea is that this is going to have its own special name. The other thing that I want to point out here is that this may or may not be confusing to you. But if I just take this molecule and turn it a little bit, if I just sort of rotate it a little bit, this thing is the same molecule as this one that I've drawn over here. So the idea is that this molecule has a different name than this molecule, because they are actually different. The atoms are attached to each other in different ways between here and here. However, this molecule that I've drawn, that I'm circling here, is identical to this one. Even though this one is rotated relative to this one, the atoms are attached to each other in the same way in both molecules. So the idea is that even though they are rotated from each other, these two things have the same name. They are the same type of molecule. And that may seem to be a silly point to make at this point. Obviously, for some of you, this may be obvious, that even though this is rotated a little bit, it's obviously the same molecule as this one, so they should have the same name. You'll see that might not always be so obvious, however, as we progress. So again, this unique naming of different molecules is going to get a couple of sections all by itself. So I just want you to be aware that this is yet another way of unambiguously describing molecules, especially organic molecules.